In the summer of 2004, on a barren island above the Arctic Circle, a paleontologist knelt beside a slab of 375-million-year-old rock and found something that shouldn't have existed: a fish with wrists. Neil Shubin had spent 6 years searching for this exact creature, betting his entire career on a single idea: that somewhere in rock of this precise age, in what used to be a tropical river delta, there was an animal caught in the act of becoming something else. He was right. What he pulled from that hillside on Ellesmere Island would force textbooks around the world to be rewritten within a year. This is the story of Tiktaalik rosé, the fish that proved evolution could be predicted before it was found. If you think science is just about discovery, wait until you see what happens when someone dares to predict it. Subscribe now, because by the end of this video, you'll understand why this one fossil terrified and thrilled an entire field. By the early 2000s, evolutionary biologists had a problem hiding in plain sight. They knew fish had eventually given rise to four-limbed land animals, tetrapods, but the fossil record had an enormous gap. On one side sat clearly aquatic fish like Eusthenopteron, fully finned, gilled, and river-bound. On the other side sat unmistakable early tetrapods like Acanthostega, with digits and limbs suited to shallow water and mudflats. Between them lay roughly 20 million years of missing evolutionary history. Scientists called it the gap, and for decades it was cited by skeptics as a weakness in evolutionary theory. Neil Shubin, then at the University of Chicago, believed the gap wasn't a flaw in the theory. It was a location that hadn't been searched yet. Using geological maps of ancient river systems from the Devonian period, he calculated exactly where rock of the right age, laid down by the right kind of environment, should be exposed at the surface. The answer pointed to the Canadian Arctic, Ellesmere Island, one of the most remote and hostile places on Earth. The hidden truth of paleontology is that most fossil hunting isn't luck. It's prediction, followed by brutal, unglamorous labor. Shubin's team, working with Ted Deichler and Farish Jenkins, didn't wander the Arctic hoping to trip over something. They read 375-million-year-old geology, like a map to buried treasure, cross-referencing sediment types that indicated ancient river deltas, the exact environment where a fish adapting to shallow water and occasional land exposure would have lived and died. Between 1999 and 2004, the team endured 4 field seasons on Ellesmere Island, flown in by chartered aircraft, living in tents through temperatures that dropped below freezing even in July, sharing the landscape with polar bears that occasionally forced work stoppages. 3 of those seasons produced almost nothing usable. Funding was tight. Colleagues questioned whether the gap could ever be filled by direct discovery rather than inference. Then, on July 4, 2004, later corrected in retellings, the specimen was actually found earlier that field season and confirmed over following weeks. Technician Jason Downs spotted the snout of a flattened skull protruding from a rock face. What followed was days of careful excavation with awls, glue, and Arctic patience, extracting a skeleton that would turn out to be nearly complete: skull, ribs, and critically, a forelimb containing a shoulder, elbow, and wrist, bones that belonged by every anatomical rule to a fish that could do a push-up. Before Tiktaalik, the transition from water to land was understood only in outline. Paleontologists had Eusthenopteron on one end and Acanthostega and Ichthyostega on the other, described by Swedish and Danish researchers across the 20th century, most notably through the fieldwork of Erik Jarvik and later Jennifer Clack, whose 1990s work in Greenland had already begun narrowing the gap from the tetrapod side. But no specimen bridged both anatomies convincingly enough to silence debate. Museums displayed the 2 forms side by side with a conspicuous blank space between them, a placeholder for a creature scientists were confident existed, but had never held in their hands. Textbooks used the word presumed more often than paleontologists were comfortable with. The absence wasn't just a scientific inconvenience. It was a public relations vulnerability, seized upon in debates over evolutionary theory in American classrooms throughout the 1990s and early 2000s, where the missing link argument was often deployed as though absence of a single fossil undermined the entire framework built on thousands of others. The breaking point came not with a single spectacular find, but with the moment Shubin's team realized what they were looking at, once the rock was finally split open in the field lab back in Philadelphia. The skull was flat, like a crocodile's. Useful for an animal peering above water's surface, the neck could move independently of the body, a trait absent in true fish. But the forelimb was the discovery that mattered most. Inside the fin were bones directly homologous to a human humerus, radius, and ulna, arranged with a functioning wrist joint capable of bending to support weight. This was not a fish with a leg. It was a fish whose fin contained the internal architecture of a leg, still webbed, still built for swimming, but mechanically capable of propping the animal up on a riverbed or muddy bank. Shubin later described opening the field jacket and seeing the flat skull for the first time as the moment he understood, before any lab analysis, that they had found exactly what the prediction demanded. If you've ever wondered what it feels like when a theory built on paper meets physical proof pulled from stone, that was this moment. And it's exactly the kind of verified turning point this channel exists to document. So if you want more of these, the subscribe button is right there. Discovery did not mean instant acceptance. Preparing and analyzing the specimens took nearly 3 more years. Much of it silent, methodical lab work, far from any camera. Skeptics inside and outside the scientific community questioned whether a single well-preserved animal could really represent a broader evolutionary transition, or whether Tiktaalik was simply an unusual dead-end species, an evolutionary experiment that left no descendants, rather than a genuine ancestor-adjacent form. Journal reviewers at Nature demanded rigorous comparative anatomy before publication, cross-checking every joint against both fish and tetrapod specimens held in museum collections from Sweden to Pennsylvania. There was also the quieter, more personal doubt. Years of Arctic expeditions, funded by the National Science Foundation and the National Geographic Society, had produced for 3 seasons almost nothing. Team members have since described the psychological weight of returning empty-handed, aware that Arctic fieldwork seasons are brutally short, and each failed summer meant waiting nearly a full year for another chance. On April 6, 2006, the paper finally appeared in Nature, authored by Deichler, Shubin, and Jenkins, formally naming the animal Tiktaalik rosei, Tiktaalik, borrowed from the Inuktitut word for a large freshwater fish, chosen in consultation with Inuit elders on Nunavut's Inuit Heritage Trust as a gesture of respect for the land where the fossil was found, and rosei, honouring an anonymous donor who had helped fund the expeditions. The announcement moved through the scientific world with unusual speed. Here was an animal with fish gills and scales, yet a mobile neck, a flattened crocodile-like skull, and a fin containing a functional wrist. It could likely prop itself up in shallow water and possibly on exposed mudflats, using its forelimbs in a motion anatomically closer to a push-up than a swimming stroke. Multiple specimens were eventually recovered. Not just one lucky find, but several individuals ranging up to 9 feet in length, allowing researchers to confirm the anatomy wasn't an anomaly. The moment of unexpected humanity in this story isn't dramatic. It's quiet. Shubin has recounted that upon finally freeing the forelimb from the rock and seeing the wrist bones clearly for the first time, the reaction in the makeshift lab wasn't triumphant shouting. It was silence, then laughter, then a kind of disbelief that 6 years of educated guessing about ancient geography had produced exactly the animal the theory demanded, as though nature had been waiting patiently to be asked the right question in the right place. Within a year, Tiktaalik appeared in biology textbooks across North America and Europe, illustrated beside Eusthenopteron and Acanthostega as the missing middle chapter. It became a centerpiece exhibit at the Field Museum in Chicago and the Academy of Natural Sciences in Philadelphia. Creationist organizations, which had previously used the gap as a rhetorical weapon, were forced to shift their arguments, since the specific missing evidence they had cited by name now sat in a drawer in Philadelphia, catalogued, peer-reviewed, and replicated across multiple specimens. Perhaps most tellingly, the prediction itself became a teaching tool. Professors began using Shubin's geological reasoning, read the rock, not just the bone, as a model for how modern paleontology actually works, a discipline of testable hypotheses rather than passive digging. Tiktaalik discovery didn't end research into the water-to-land transition. It accelerated it. Subsequent expeditions and reanalyses of older museum specimens, including trackway fossils from Poland, dated even earlier than Tiktaalik, revealed that the transition to land was messier and more gradual than a single clean lineage, with multiple lobe-finned fish experimenting with similar adaptations over millions of years. Shubin went on to write the best-selling book, Your Inner Fish, and a companion PBS documentary series, translating the anatomical connection between Tiktaalik's limb bones and the human arm for a general audience. The same wrist bones, repurposed by 375 million years of evolution, now let you hold a phone, type on a keyboard, or turn a page. The specimen itself and its cousins remain housed at the Academy of Natural Sciences of Drexel University in Philadelphia, still actively studied. What began as a bet on geology and patience became one of the most cited transitional fossils in modern biology. Tiktaalik answered one question that had haunted evolutionary biology for over a century. But it raised a harder one that scientists are still sitting with. If a single specific prediction about rock strata and river deltas could lead directly to one of the most important fossils ever found, how many other missing links are still out there? Not missing at all, just unsearched, waiting in some overlooked stretch of exposed stone for someone patient enough to do the math first. Somewhere on Earth, right now, there's probably another gap in the fossil record with its own coordinates already calculable. If anyone's willing to spend 6 Arctic summers finding out, what do you think is still buried out there, waiting to rewrite what we know? Tell me in the comments, and if this kind of verified, deep dive history is what you come here for, subscribe. There's more of it coming.